Okay, now I'm explaining about materi, the concept of activity. The mathematical discussion in the preceding chapters have been limited to systems that behave ideally. The system were either pure ideal gas or ideal mixture or gas, liquid, and solid. Many of the systems described in chapter 15 are not ideal. The question that arises is how are we to deal mathematically with non-ideal system? The system are handled confinedly using the concept of fugacity and activity first introduced by G. N. Lewis. The chemical potential of component and mixture is in general a function of temperature, pressure, and the composition of the mixture. In gas mixture, we write the chemical potential of each component as the sum of the terms in this formula 16.1. The first term is a function of temperature only, while the fugacity Fi in the second term might depend on the temperature, pressure, and composition of the mixture. The fugacity is a measure of the chemical potential of the gas I in the mixture. In section, a method by evaluation. The fugacity for a pure gas we described. Now we will confine to our attention to liquid solution, although most of what is said can be applied to solid solution as well. For any component I in any liquid mixture, we write in this formula 16.2. Okay, next. To ask equation 16.2, the significance of the function temperature and pressure must be accurately described. Then AI has a price meaning. Two ways to describing temperature and pressure are in common as which leads to a different system of activity, and either system the activity of a component is still a measure of its chemical potential. Next materi, the rational system of activity. In the rational system of the activity, temperature and pressure is identified with the chemical potential of the pure liquid. Temperature and pressure in this equation 16.3. Then equation 16.2 becomes equation 16.4. Okay, in this, next, as xi to 1, the system comes nearer to being pure I and must approach so that this is okay, you can see. Next, using this infinite equation 16.4, we have this or this in this equation point 16.5. Therefore, the activity of the pure liquid is equal to unity. If we compare equation 16.4 with the in an ideal liquid solution in this equation 16.6, by subtracting equation 16.6 from equation 16.4, we obtain an equation 16.7. The rational activity coefficient of IEI is defined by this equation 16.8. With the definition equation 16.7 becomes equation 16.9. Okay, which show that in AI measure the extent of the deviation from from the relation in equation 16.5 and the definition of yeah, we have equation 16.10. Okay, the rational activity coefficient are confined for the system in which the mole fraction of any component might vary from 0 to unit mixture of liquids such as actun on chloroform. For example, 1. The rational activity volatile substance. The rational activity of volatile constant in a liquid mixture can be readily measured by measuring the particle pressure of the constant in the vapor passed in equilibrium with the liquid. Since at equilibrium, the chemical potential of each constituent must be equal in the liquid and the vapor phase. We have equation 16.4 for an assuming the gas is ideal component I having a particle pressure. We can write this. I'm sorry. We cannot write this or this equation 16.11. Okay, and next materi, colligative property. The colligative property of a solution of involatile solutes are simple expressed in terms of the rational activity of the solvents. 1. Vapor pressure. If the vapor pressure of the solvent of the solution is pressure and the activity of the solvent is A, then from equation this. Okay. Next, 2. Freezing point depression. If pure solid solvent in equilibrium with solution, the equilibrium condition becomes using equation 16.4 or this. Next, repetition of the argument in section. Finally, in this equation 16.12, which is the analog of equation for the ideal solution. Now, from vapor pressure measurement, the freezing point can be calculated from equation 16.12. Conversely, if the freezing point temperature is measured, it can be evaluated from equation 16.12. Next, boiling point elevation. The analog argument shows that the boiling point is related to delta H, vapor, and T0, the heat of vaporization and the boiling point of the pure solvent by this formula. Next, osmotic pressure. The osmotic pressure is given by formula this 16.14, which the analog in equations 16.11, 16.12, 16.13, and 16.14. AI is the rational activity of the solvent measurements of any colligative property yields value of the through this equation. And the last materi, the practical system. The practical system of activity and activity coefficient is useful for solution in which only the solvent has a mole fraction or unity. All the solutions are present in relatively small amounts for such a system. We ask the rational system for the solvent and the practical system for the solute. As the concentration of solute becomes very small, the behavior of any real solution approaches that of the ideal dilute solution. Using the subscribe to identify the solute, then in the ideal dilute solution, formula this 16.15. For a solute, equation 16.2 becomes equation 16.16. This, if we subtract equation 16.15 from equation 16.16 and set temperature and pressure, and then 16.17. The identification, temperature and pressure. We define the practical system of activity. The practical activity coefficient Yg is defined by equation 16.18. Equations 16.17 and 16.18 show that is a measure of the departure of a solid from the behavior on ideal dilute solution. Finally, the solute must behave in the ideal dilute y so that in equation 16.19 and the last is follow that Ig equally Mg as Mg equally 0. That's for the chemical potential of solute in the practical system we have. And this formula, equation 16.20. 1. Volatile solute. The equilibrium for the distribution of volatile solute between solution and vapor. Using equation 16.20 and assuming the vapor is ideal, we have this, you can see. Science and depend only on temperature and pressure and not on composition. We can define a constant Kj, which is the independent of composition by this. The relation between pressure and I becomes this. Equation 16.21. The constant is a modified Henry's law constant. If K is known, value of Ig can be computed immediately from the measured value of Ig. Dividing equation 16.21, we obtain and this 16.22. Measure value of the ratio pressure or plot as a function of Mg. The curve is extrapolated to Mg equals 0. The extrapolated value of Pg or Mg is equal to K epsilon G since Ag or Mg equals 1 as Mg to 1. And this, okay, next, in volatile solute, colligative property and the activity of the solute. In section 16.3, solvent, this solvent and the solute. They are related by the Gibbs-Dunn equation. This temperature and pressure constant. Difference keeping temperature and pressure constant, we obtain this. And using the value in the Gibbs-Dunn equation, we have this. And this, of course, and this is temperature and pressure constant. Next, dividing keep and temperature and constant, we obtain this. Okay. But into Rn, where M is the molar mass of the solvent and M is the molarity of the solute, therefore this. Next, freezing point depression. This different in equation 16.12 and using the value for in a given by equation 16.23. This. Okay. And this to arrange in the terms of the more responsive function, we introduce the osmotic coefficient y mean g divided by this. This equation 16.25. And using equation 16.18, we set A2, this, and this. And using the two relation in equation 16.24, it becomes this. And the last, this equation is integral from m equals 0 to m. At me m equals 0, I2 equals 1, and g equals 0. We obtain this. This equation 16.26.